Hi, this is a demonstration of using InterFringe to trace fringes in a static interferogram. First we'll open a static interferogram that's suitable for tracing fringes. Now, in order to do this, this is an A-sphere, and in order to characterize an A-sphere properly, it's very important to set up a boundary that's accurate. If the boundary is decentered significantly, or if the size of it, the radius of the boundary is wrong, then the characterization of the wavefront is not going to work very well, because the decomposition into different aberrations depends on accurately knowing where the center of your reference is. And so that's what we're doing. First, we set up a boundary. The boundary has an obstruction because this is an annular optic. So we set up an outline on the outside and then a boundary. Now we're going to do fringe tracing here. We've got a black and white version of the interferogram now that has the boundary centered. And first thing to do is to blur this thing a little bit. It's kind of grainy, so not a really good quality image. So now I'm going to pick a fringe. I'm going to pick a fringe at basically the top of the surface, and I put one point on the dark fringe. Clicking auto trace tells the program to attempt to find the contour of that fringe, and so you can see it's done that. I'm going to click next. That tells the program that we've gone to a new level. This next level is going to be one wave different in height from the one we just traced. I'm going to trace this one. Now this interferogram has a few problems. This feature down here in the bottom is a clip that was used to hold the optic in this test stand, so that stopped the trace in that direction. As long as I don't, I'm clicking an eraser here to wipe out some bad points. As long as I don't click next, the program assumes that I'm still on the same fringe. So now we're starting fringe 3. Place a point here, trace, and we'll trace down here. It's often necessary to make multiple subtraces on a single fringe. Now I'm going to go ahead and add a couple more fringes. I'm going to trace one here, and just to show you something that sometimes necessary, especially in an optic like this that has a obstruction. This thing can only trace part of the fringe because that's all that's there, but if we click on the other part and then click trace again, then it traces the entire fringe. It's interrupted because of this presence of this obstruction. Alright, well, I can keep going here. I can trace the entire optic, but I've already done this. I've already traced these fringes once before. And so I'm going to open that a file that I saved those fringes in last time. Now, if you look at this, the fringes are all traced. The blue indicates the current fringe, the active fringe, and you can see this is number 5 of 16. The other fringes are all traced. Now, I started on the other one and the other one, but sometimes you have to trace them in the order that's easier, and so you can reverse the fringes after that. Reversing the fringes makes this the bottom fringe, and they would go in the reverse order. So, in fact, this is the correct order, because this top circle is the very top part of the optic. It's the highest contour in the contour line set. Now, in order to get a model of the surface, I need to use some kind of polynomial fit, and I've got three choices here. One is standard Zernike polynomials, which are polynomials that are orthogonal on a circular aperture. Annular Zernike polynomials, which are a modified version of the standard ones that are orthogonal over the annular region that we have here, or cubic spline interpolation. Annular Zernike polynomial fit is the best choice because it can model the optic in terms of aberrations that are commonly used to characterize optical wavefronts. So I've got all the Zernike polynomials here. The active ones, the ones that are going to be used to calculate the surface model, are checked. All the ones with no check marks are going to be ignored. Piston, tilt about y and x-axis, defocus, those are all obviously artifacts of the alignment. Coma is also, third order coma is also an artifact in general. I mean, it's possible they could be part of the optic, but very unlikely. So we're going to ignore those, and now we can plot a model of the wavefront. So here's a model of the wavefront. This is a parabolic optic, and it's measured relative to the spherical surface that's best fit. So as you can see, as I scan around this you can see the different the variation in height. There's a certain amount of astigmatism present in this optic. And I can create a report here. Creating a report. We're going to create it in docx format. Best to create a folder for the report, a separate folder for the report, because it stores temporary files, image files in there. And it's nice to have them all in place. And now we're going to save it. I'm going to open it in LibreOffice, and there it is. In the report, there's a header with the part number, serial number. There are overall results of the wavefront analysis, breakdown into sidal aberrations and Zernike polynomials, and a 3D model of the surface. All right, thank you very much. This concludes this part of the demonstration of InterFringe. The other features are demonstrated in separate videos. Thank you.